Thank you. Thanks for the introduction. I'll be presenting our attempts at making SPH a viable tool for compressible flow simulation, especially for aerospace applications. So why SPH? The below images you can see. So there are these booster rockets separating from the main rocket body. So there is fluid solid interaction. There is moving bodies. There are shocks reflecting from moving bodies. So all of this is would be easier to do with SPH than traditional CFD method. So, but SPH comes with its own disadvantages. The boundary treatment method is not robust. And since the particle density is tied to the actual density, low density wakes are actually resolution deficient. And there is this convergence conservation trade-off. So we'll be focusing on mitigating these disadvantages of SPH mainly. So these are my governing equations, simple Euler equations, no viscosity, plus an equation of state. That's all. These are my SPH discretized governing equations. SPH discretized governing equations with some stabilizing terms. I won't dwell too much on these as this has been introduced yesterday and day before. Then these are SPH discretized governing equations with transport velocity formulation. So if we move our particles with the velocity u, that conforms to a Lagrangian description. Now, sometimes it's beneficial not to move our particles with the Lagrangian velocity, but to move it with a slightly different velocity, u tilde. So when we wish to do that, we add these couple of terms to our governing equations to make it all consistent. So this is transport velocity formulation, where u tilde is the transport velocity and delta u is the correction velocity, which is the difference between the transport velocity and the Lagrangian velocity. This is how wall boundaries are usually treated in SPH. We use ghost particles. So we directly, so there are two ways of going about it. We either directly interpolate properties from fluid particles to ghost particles, or we interpolate properties from fluid particles to ghost mirrors, and then copy over those properties to ghost particles. So, and then we flip the velocity about the interface normal. By the way, I'm talking about pre-slip boundary conditions. Anyway, it's inviscid, so yeah. So turns out this does not work for compressible flows. This leads to leakage. Particles leak from the boundary. So the problem here is that when we interpolate density, what happens is m by rho, which represents the volume that a particle is supposed to occupy, is not consistent with the volume that the ghost particle should actually have. So, however, this is not a problem with the incompressible SPH or weakly compressible SPH because, well, the density doesn't vary too much over there. So for this, it's very simple. We propose a very simple fix. We ensure that the ghost particle volumes remain constant, and then we it fixes the leakage issue. So, I mean, literature is really scarce for these kind of problems, but we were able to find someone who, one work which actually used some Lennard-Jones-like repulsion to move the particles away from the boundary. So we compare their shock angle error, beta is the shock angle, so with ours, and we are consistently below 1% error, and much better than theirs. So turns out ghost particle volume constancy does not fix all problems. We still can have leakage issues when the particles, when the ghost particles and the fluid particles do not have a very inconsistent spacing. So what we do, I mean, again, this is we basically we have insufficient repulsion. So what we do about this is we introduce a correction velocity, and through this correction velocity, we basically shoo away the particles which are not respecting the boundaries. And this is consistent because we are doing it through transport velocity formulation. And with these, we are able to simulate a bunch of classic fluid dynamics problems where we have a convergent divergent nozzle where the flow is accelerating smoothly. Then we have this 2D shock tube where we have a shock which goes, hits the wall, reflects back. We have a forward-facing step where there is multiple shock wave interaction, oblique shock interactions. We have a cylinder cone flow ahead of a blunt body where we have bow shock forming ahead of a blunt body. We have a biconvex airfoil where it's flow around a slender body. So all these work right now. We can also do moving bodies without much effort. Basically, we just have to move bodies. That's all. I mean, so this is a rotating square projectile case from Elmer, which is another compressible flow solver. So this rotating square, it rotates to and fro like this, and it's in a flow. So we compute the forces of the body and get a very good match. So, but again, it's not all perfect still. We do this double Mach reflection problem, and we see numerical issues, artifacts over here again. So the way to solve this is, for solving this, we introduce adaptivity. So we looked at a lot of literature on adaptivity. We end up with these three, we narrowed it down to these three papers. So I list the advantages of these two groups of papers. And what I'll try to do now is merge the advantages of both the papers so that it's better actually. So this is how the splitting works. In 1D, a particle splits into 2, in 2D into 4, in 3D into 8. The size A is given by this expression. Number of offspring depends on the dimensionality of the problem given by this expression. Once we have that, volume is equally divided, density is linearly interpolated. We have volume and density, then we have mass also. Velocity is linearly interpolated, and then we have a correction term. So this correction term ensures conservation. Same for energy, and then we get the pressure from equation of state. So how the splitting and merging works is we assign each particle a reference volume, and when the volume of the particle goes 1.6 times the reference volume, above that, we split the particle. When it is below 0.6 times the reference volume, it starts looking for a merge partner. So that's how splitting and merging, that's the threshold for splitting and merging. It's borrowed from Sun et al. Without any change. Merging procedure is similarly borrowed from this paper without any change. For local adaptivity, we use volume rather than mass. It's borrowed from Hafto et al. And for solution adaptivity, it's again borrowed from Hafto et al, the general procedure, but instead of vorticity, we use a shock indicator. And for shifting, we use a commonly used Fickian-based shifting which is commonly used in SPH. And we limit the shifting using the shock indicator. So there is this piston chamber case where there is a rectangular chamber and the piston moves back and forth. So the pressure increases as the piston moves in and reduces as it moves back. So these are the results. It's in very good agreement. Conservation is nice, very good. So again, now we come to a problem where again lack of adaptivity is a issue. So here, this is a shock diffraction problem. So initial condition is that, so there is a backward facing step. Right above the step, initially, there is a shock. And as the time progresses, the shock moves and there is, and leads to the formation of this structure. So in this region, there is actually very low density and so low number of particles, and hence it's poorly resolved. Also, there are these spot-like structures which form at the interface of the contact interface. So for this, when we introduce adaptivity, this problem is solved. We have some high frequency noise here, but it's mostly solved. Similarly, the double Mach reflection problem, which I showed you earlier, that's also mostly solved. So now I'll tell you how our adaptive resolution works. So solution adaptivity works. So with solution adaptivity, we are aiming to resolve shocks better. So we refine particles in the vicinity of a shock. So you can see the particles get refined over here, again refined over here, and then this is the shock. I'm plotting negative divergence of velocity, and you can see the actual negative divergence of velocity is higher for the adaptive resolution case. So the way we do this is we identify the minimum of divergence of velocity within the domain, and we normalize our divergence with this, and we call it var sigma. We spread this var sigma around, and then if this var sigma is greater than a threshold, we mark those particles with a minimum spacing, and then minimum reference spacing. And then we form these bands through algorithm 1 of Haftu et al. So these bands are in steps of 1.2, as in the innermost band is delta S min. The next band is 1.2 times delta S min. Next band would be 1.2 square times delta S min, and so forth until it reaches the maximum reference spacing. So again, so as the particles come in and enters one of these bands, they split and they pass through the shock and then they merge and they merge. So we also introduce shifting to regularize particle distributions, but we limit the shifting near the shock so that the shocks are not shifted. Shifting works very well in smooth regions, not near the shocks. So we limit the shifting again using our shock detector. And then we are able to solve this by convex airfoil problem very nicely. So we can see the orange line denotes where the reference volume of all the particles is constant throughout the domain. And the green line where the reference volume is near the body and near the shocks is 1/4 the reference volume of the coarsest reference volume. So doing this actually makes our results much better. So as a proof of concept, we also show that we can do this in 3D as well. So we use this simplified geometry of Apollo re-entry capsule. We do flow over this in 3 dimensions. So we have results. It's a thin 2D slice of the 3D flow field. So without adaptivity, we see behind the shoulder, it's really, there are no particles around here. It's very poorly resolved, but with adaptivity, it's nicer. And the physics is also captured nicely. We expect this reattachment shock to be normal to the body where it is attached, because, well, when otherwise, I mean, when very near the body, we cannot afford to have a flow deflection, which is actually captured very nicely with adaptivity. So we can do this in 3D as well. That's been my talk. Thank you. So to summarize, when ghost particles are being an ineffective partition of space, we ensure ghost volume constancy. For inadequate repulsion due to our equation of state, we introduce a leakage shield. And for resolution deficiency and errors due to inconsistent spacing of particles, we employ a adaptive resolution procedure. All our work is open source. Manuscript for the boundary treatment is on archive already. The other one will come soon. Code is also open source, and we also use open source tools. Thank you very much.
So when you do this adaptive refinement, it's common in SPH to perform relaxation after the refinement, so that the newly placed particles are more evenly or regularly distributed?
Yes, it is. That's what I showed you shifting. That's what it does. It's actually relaxed. Yeah.
Numerical overhead do you introduce for this refinement and the search for points which may need to be refined or merged?
For a 2D simulation, it's about 10 to 15% numerical overhead. But again, it's actually not an overhead, because we can have very coarse particle distribution outside. So it actually reduces our time. Yeah.
Thank our speaker again.
Thanks.
Other way around. Yes. Yes. This feature is Nicolas Police. It's going to talk about moment-based realization of positive events. I think also this one. No, just click on the screen if it doesn't move. Where? Just click anywhere on the screen. Done. Okay. Okay, so I think we're good. Yeah. Thank you very much for the introduction. So good afternoon, everybody, and thank you for attending my talk. So my name is Kalikounis Nikos, and I am a former graduate student of Professor Carlin. And today I will talk about my work related to the particles on demand method. So the history of computational gas dynamics goes back to the 1950s with seminal work of scientists like von Neumann, Brand, and Godunov. So the field extends well beyond academia, and it is significant for both science and technology. So here you can see some examples. Let me find the laser. I cannot. Okay. Yeah. So you can see indicative examples with astrophysical flows, such as supernova explosions. Then we can also have optimization of aircrafts, able to operate all the way from subsonic to hypersonic regime. and also the design of space vehicles and their propulsion systems. So kinetic theory offers a unique approach to model such flows, with the lattice-Boltzmann being one of the most popular methods. So the key component of LB is the finite set of velocities, which is used to discretize phase space. So the fictitious LB particles, they have velocities that are coming from these discrete ones, in general, following a scaling and a shift operation. So this is equivalent to an understanding of the particles relative to a reference frame with a given frame temperature and frame velocity. Conventional LB assumes that the discrete particles are equal to the velocities, and that implies that a uniform frame at rest and at constant temperature is applied throughout the domain. This is a simple choice and straightforward, but it is restrictive in terms of operating range. So the good news is that we have more freedom in selecting the reference frame. So for example, shifted lattices were introduced by Frappoli, and this amounts to a uniform velocity shift in the entire domain. And this works well for unidirectional flows, but in general, it fails for generic situations with strong variations in flow velocity or temperature. A natural approach to avoid these limitations is to relax the use of a fixed frame and instead use a variable one adapted to the local flow conditions. And this adaptive reference frame is the core idea of the Pond method. So given that Pond operates with an adaptive frame, it is crucial to establish a representation of populations with respect to different frames. So this is termed a reference frame transformation and is the backbone of Pond. So now we assume that we are given a vector of populations defined with respect to a certain frame called lambda. And from that, we can linearly construct populations as matrix multiplication. So now to connect with a different frame, here we call it as lambda prime, we impose that the moments should be the same, irrespective of the frame that is used for the calculation. This is the moment matching condition, and we also say that the moments are frame invariant. So this condition leads to a well-defined linear relationship between the populations of the different frames. The moment matching condition can be further relaxed and instead require that a certain subset of the moments is frame invariant. And this regularization is essentially matching condition can be enforced by expanding the transformed populations in a finite Hermite series, so a Grad's projection, with a cutoff order at order n. So the transformation in general here is crucial for frames that differ by large values, for example, near the shock discontinuities, and this can help stabilize simulations with very large Mach numbers and temperature ratios. So Pond was originally realized with a semi-Lagrangian discretization scheme, which is very similar to the LB algorithm, but here it is adapted to accommodate off-lattice velocity sets. And so the update rule is again executed as a series of streaming and collision steps with additional interpolations that take care the off-lattice departure point and frame transformation that connect the different frames. So the Pond has been applied with multi-phase flows, rarefied gas dynamics, simple detonation modeling, and also higher-order spatial discretization schemes. However, there is a drawback with the semi-Lagrangian Pond, and this is that we have a loss of conservation, which hinders simulations of high Mach. And this is why finite volumes method were developed later, with first attempt following the discrete unified gas kinetic scheme, or DAX in short, introduced by Zhao Guo. And later, other Eulerian schemes were developed, which together with DAX, they both address the regime of high Mach compressible flows. So the natural conservation of these finite volume schemes enable the simulation even at the presence of very steep discontinuities. However, the cost is that we have slightly more complicated algorithms and more frame transformations per node update. So first, I will review the Pond DAX code. And so here we divide the physical space into control volumes, and we keep track of cell center populations, which they represent cell averages. The discretization of the Boltzmann equation we use the midpoint rule for the flux term and the trapezoidal rule for the collision. And this discretization leads to this highlighted update equation. And as you see, first, there are two Fs that participate in this equation. So the original one, but also a transformed one, which is similar to the conventional LB, is introduced to remove the implicitness of the scheme. So the key term here in this equation is the flux populations. So you can see them here in the interface and at half time step. And the alpha and beta are parameters which are generally dependent on the time step and on the viscosity. So the drawback here is that to complete one time step, we need several frame transformation between the frame of the cell center and the frame of the adjacent interfaces. And this is why here in this work, we try to reside as much as possible in the moment space and reconstruct temporary populations to retrieve the necessary fluxes. So with this technique, we try to have the benefits of obtaining the fluxes through population, but minimize the number of frame transformations. So here in this setup, we keep track of moments which are stored in the cell centers, and the previous update equation can be written in the moment space like that. And again, the key term here that is missing for the update are the fluxes of these moments. So now the question is, how exactly do we obtain these fluxes? And so the answer is that what we need to compute the fluxes are these populations here at the interface and half time step. And what we know are moments at previous time step level and at the adjacent cell centers. So we connect everything together by a half time step LB step, which essentially relates the flux populations with the ones at the departure points. So to realize this flux calculation, first we need to set the reference frame for the LB step. And for that, in this work, we use the average frame between the two adjacent cell centers. Then, based on the moments that we have and using the grad expansion, we reconstruct the necessary populations, so at the centers here, and also calculate the slopes, so using slope limiters. And so here you can see again the overbar notation, which again stands for populations which are essentially linear combinations of the original and the equilibria. And again, they are used to make the equations be written in an explicit form. So now what is left is to linearly reconstruct the populations at the departure points here and complete the LB step. So with that, we have the populations that are necessary to compute the moments of interest. And with some proper tuning between equilibria and the moments, we finalize and retrieve the actual moment that we need to close the update. The kinetic model that we're going to use for the simulations here is the two population model, where the second population, designated here as G, carries part of the internal energy and enables a flexible adiabatic exponent. So the conventional BGK collision here is implemented, and we supplement it with a quasi-relaxation process and an additional relaxation time. So the two times are linked with the viscosity and the thermal conductivity. And by proper tuning, we can simulate fluids with different Prandtl numbers. So here, according to the requirements of the application, the model can also be simplified by disabling the quasi-relaxation process for the Euler cases, let's say. And for this, to retrieve the fluxes, we use moments up to third order and the D2Q16 lattice. And for full Navier-Stokes Fourier system, we store moments up to fourth order and we use the 25 lattice. So let's see now some results. And we start the validation of the scheme with Euler flows, starting with one-dimensional benchmark cases. So here you can see the SOD and the lax tube, which are typical Riemann problems that involve flows with mild discontinuities. So these simulations are shown with a resolution of 600 points, and we see a quite good comparison with the analytical solution. The last one is the Schuosser problem, which is more demanding. And here we have a Mach 3 shock wave, which interacts with a perturbed density field, and that leads to discontinuities and the formation of small structures. So the results are shown here for 800 points. And in general, we see that we capture the shock locations and the high frequency waves quite good agreement. And we have a small underestimation of the amplitudes because of the numerical viscosity. We continue here with the two blast wave interaction problem. So it was introduced by Woodward and Colella in 1994. And here in this setup, the domain is initialized with uniform density and zero flow, and we impose three different pressures. So the highest is at the left part of the domain, a medium pressure is imposed at the right, and the lowest one at the middle of the domain. And this setup, it develops two strong blast waves which interact in a complicated manner, and especially in the time of the collision, we have very strong gradients that emerge. And this is why this specific benchmark is a typical benchmark for probing robustness and accuracy. So here we can see the results for resolution of 800 points, where in general we see quite good agreement with the reference. So the final 1D problem is the shock structure for a Mach number of 1.2. So here the domain is initialized according to the ranking Hugoniot condition, and the solution is developed until we reach steady state. So in the top right plot, you can see here the density and the temperature that evolve through the shock. And the bottom shows the corresponding results for the stress and the heat flux, where in all cases we see quite good agreement with the reference. And now we move on to 2D simulations, and starting with the double Mach reflection problem. So here we have a Mach 10 shock wave colliding with a reflecting ramp, which is inclined 30 degrees. And after the initial impact, we have a self-similar structure that is formed in the ramp and grows in size as the shock propagates towards the right. And here we follow the conventional setup in the literature. So we first rotate the coordinates such that the horizontal axis is now aligned with the ramp. And the tilted line here signals the initial shock front. At the left of this line, we impose the post-shock state, and at the right, the pre-shock state. And we can see here the evolution of the flow according to this specific setup. And what we see here is the magnitude of the density gradient. Finally, we show the 2D benchmark, which is the viscous shock tube case. It's a problem originally proposed by Daru and Tenot. And here we have a gas which is confined in a 2D box and initially stagnant. And then we have a partition which separates a high pressure region from a low one. And we remove the partition, and that initiates a right propagating shock wave, which induces a boundary layer. It collides with the right wall, it reflects, and then there is interaction with the boundary layer, leading to a complicated flow pattern. And the results with reference data, it's you can see them here. So we have the locations of flow features, which is in quite good agreement. And also in this plot, you can see the profile of the density at the wall, which apart from some locations, in general, it's been very good reference. And with this, I conclude my talk, and I would like to summarize the main key points of the presentation. So what we showed is a finite volume discretization of the Pond method based on the DAX algorithm, which leads to a conservative formulation. And what we stress in this work is that we should combine moments and populations such that we minimize reference frame transformation. And the model was validated with 1D and 2D challenging test cases. And for the future work is 3D implementations, curved walls, and further techniques to improve efficiency. So, thank you very much.
There is a very large machinery for solving compressible flow with a finite volume method with window schemes. So have you compared your method with this kind of more older methods? What are the advantages?
Yeah, so this work that we have showed so far does not discuss the inclusion of the more advanced schemes for reconstruction. So here the main focus was to manage high Mach flows to begin with, And extension with Windows schemes are impossible, let's say also in the DAX, without paying attention to the pond method. Also, originally, DAX started with simple schemes, and then they also improved to the reconstruction schemes with testing Windows. And so here, so far, we have not gone to that direction. And for sure, it's something that we can go in the future. But I think the main benefit in general, comparing our scheme with generic finite volume schemes, is that this method can be extended also to non-equilibrium flows, which is not the case for traditional Navier-Stokes solvers. So here we can put more moments to capture non-equilibrium effects. And we also don't have to do that in the entire domain. We can have an adaptive partition of so in the domain, we can use the high order moments in specialized regions. And so I think that can lead to a quite efficient scheme for flows that combines equilibrium and non-equilibrium flows. When I do what? When I change what exactly? I mean, yeah, I mean, it's what I would say is that if I compare, let's say, this algorithm, which is the DAX plus reference frame transformations, and I compared it with a purely DAX code, we are still in the same order of magnitude. We are not increasing the overhead too much, especially with this technique where we store moments so that we minimize the frame transformations. In older version of DAX pond, we had more frame transformations, and there we had less efficiency. But here I would say that we are on the same scale. I mean, of course, we have an overhead, but it's not that dramatic. Thank you.
Yes. It's a PDF.
Yeah. Final presentation of this session will be given by Dsfd. The 3D simulation of a supersonic compressible mixing layer using the semi-Lagrangian Dsfd method.
So thank you for the introduction and good afternoon. So I will be introducing to you a method that has been introduced previously by my predecessors, Andreas Kremmer and Dominik Wilde. So maybe you have heard of it before, but I will anyway introduce again what it looks like. It's not entirely dissimilar, but at the same time, a thing on its own compared to the other compressible LBM solutions. And I will present a novelty for the LBM, which is the compressible mixing layer at high Mach numbers, which is a standard test case to validate how good the solvers perform for compressible effects. So I will be introducing the method and the test case and some simple results. So when we look at the classical LBEs, we have in the top the general equation, and then we have the collision term, which is expressed here with the BGK collision, and below we have the streaming step. And if we put those together, we arrive at the form which actually makes the current value on the left depend on the previous time steps. And this is something that helps understand a little bit what we think like in methods, such as also particle on demand maybe, and as well as the meshless method. So if you focus still on the bottom equation, we can introduce some extra terms. So in order to vary the Prandtl number, which you can see here now. So nothing changed in the first two rows of the bottom equation, but we add an additional quasi-equilibrium, and we now don't refer anymore to F, but to H, which is just a summary of the two species G and F to also depict the internal energy. And in the top, this is something that it's easier to show on a picture. It's Lagrangian interpolation for the populations that we require. So in the bottom also you see that actually we go to X minus delta TC or Xi, whatever you want to call it. And so this in practice looks like this. So we have our arrival point and we want to look backwards in time and arrive at a space where we want to look for the observables and to find out then what the arriving populations look like. And you can see here already that we do not look at a regular grid anymore and then vary the stencil within this regular grid, but actually we also vary the way the grid looks, because like this we can manipulate a little bit the Lagrangian polynomials to make them more stable for shocks moving within this space. So usually you would have to have a neighbor search for this departure point, or you would have to know something about which neighbors to find. And in our case, this is a finite element grid, so that when you know which cell the departure point actually belongs to, you already know the weights of the Lagrangian polynomials to imply there. So the interpolation basis, it's the most stable is, or the one that we use, which has been proven to be stable, is Gauss-Lobato-Chebyshev interpolation, integration points for the interpolation. So of course this is not entirely loss-free, but it actually proves to be quite stable and quite accurate. Now, something that in the compressibility schemes is often quite difficult, and you also mentioned it in your keynote, is that you have to have a very large stencil. And in 1D, it's okay. In 2D, it's already quite difficult. But in 3D, it just becomes a bit too much. It has been executed and implemented, but it's actually quite a lot of velocity space. But because we are no longer restricted to have an equidistant stencil in our velocity space, we can do some tricks. So in particles on demand, we stretch and we rotate depending on our observables in the arrival point. In our case, we integrate in the same way in the whole space, but we apply some mathematical rules, which we can do because of the multivariate analysis. So in 1D, you would still need to have the same number of stencil lengths, but in 3D, you can actually apply some mathematical tricks, and then you arrive at a D3Q45, which decreases the computational cost a lot, and that's how we can arrive at really quite difficult problems such as the mixing layer. So the mixing layer looks a little bit like this. On the bottom right, you can see, I don't know if you can see it in back rows, but in the middle where you have the bright line, this is velocity near zero. This is the downstream velocity. So on the top, it moves to the left. On the bottom, it moves to the right. And in the middle, we have employed some fluctuations. That's why it looks a bit wavy. I don't know if you can see, but you will see later what it looks like in the end. And we employ a velocity profile. So we don't just say that it's a shear layer and there's no transition, but it's a tangential profile that we imply there. And this profile actually contains a parameter, this delta theta in the below the x2. So this is the velocity thickness, what we call momentum thickness. And later on, we can see also how this is a key observable also during the development of this domain. Next to this, we can also think a little bit differently about this. So if we look at this tangents profile, I hope it's clear enough, but we can also look at the maximum decrease or the maximum change in velocity across along the shear layer. So this is something that I will show as an equation later, but maybe it's easier to see in this way of depicting it. So we need to put some disturbances so that this mixing layer actually develops over time. And the way that has been proven already before is to impose the velocity potential. So this is what we call psi on the top. And it's just a normal distribution between -1 and 1. And it's a scalar in space. And then afterwards, in the fourth line, you see that we just take the curl. And like this, we arrive at a sinusoidal disturbance, which is actually quite important. And in the middle, you just see that we scale it. On the one hand, we want to have high energy in low wave numbers, and on the other hand, we want it to be restricted in space to this to the mixing layer. And so we just do some things there, which is very similar to what has been done in the DNS before. We can also do some things which is a huge advantage of the method, but in our case, it's more or less the same things happen in the whole domain, except on the top and on the bottom, where you have, or you're supposed to have, a very equal flow. So I don't know if you can see it so clearly, but we basically stretched the grid. So you can see here that the grid actually becomes a bit coarser towards the outsides. This is something that we can do in this method. It's a lot larger advantage in other cases, such as the flow around an object, where you have very, or around shock waves, where you can predict which areas you need to refine better. So this is around 15 million grid points, just to give you an idea. And this was possible mostly also because of the cubature rules that you can apply there. So the way it looks like on the left, you can see the downstream velocities. So again, it's here it's to the right on the bottom, to the left on the top. And on the right-hand side, you can see the vorticity. And this develops over time. So you can see that this is a very nicely looking turbulent behavior in the middle, and then it stretches outside. And what we want to look at now is the thickness itself and the way the thickness develops over time, because we can arrive at a state where the way the things change, once you normalize with some constants that you know before, you can actually find that it has a self-similar behavior. So the key observables, as I mentioned before, the one on the top, the vorticity thickness, is just the steepest decline in averaged velocity. And this is proportional to the momentum thickness, which is actually a bit more rigorous observable. So that's why we use that. And the growth rate, so the rate of change of this thickness. And you see here that you have the fluctuations that you look at. So you take the velocity difference between the top and the bottom layer, and you take the fluctuations. And once you imply these, you can arrive at this key observable, which changes over time. And the way it changes over time, even during or especially during the self-similar state, this is dependent on the Mach number. And so this is what we see here. So on the left, you have the quasi-incompressible state. And on the right hand, you have larger than speed of sound Mach number, and so, or larger than 1 Mach number. And you normalize time generally as tau, because the velocity difference between the top and bottom layer, or outside and inside layer, it varies in the experiment. So that's why we use some normalization there. And once we compare those growth rates, so the steepness of this change, across Mach numbers, we can arrive at this depiction. So there has been a curve proposed to show roughly how the growth rate decreases with higher Mach numbers because of compressibility effects. And you can see that this compares very well to the literature. This is both experimental and numerical results that you can see here. As well, you can look at the average velocity profile. So this is from left to right, it's downstream, from bottom to top, so across the shear layer, and in the, let's say, extra space. Oh no, this is the shear. So this is the not an average profile, but it's actually the shear between the downstream velocity and the cross-stream, the cross-shear layer velocity. And this also compares very well with the literature. you have a peak in the middle, which you would expect, and then you normalize also the distances. You normalize over the current shear layer thickness. That's how you arrive at this profile, which is actually consistent over time in this self-similar state. So the shear layer grows, but you always normalize the thickness of the shear layer, and across the thickness of the shear layer, you always see the same profile. So when you compare with more marked numbers, literature is often only restricted to the peak of those profiles. And so that's why I compare here. So you can see that those peaks also align very well with the literature, although you have to say that it has to be mentioned that the literature is also not quite on the same terms not in all of the cases at least. So this is always the dependence on marked numbers, right? So the SLLBM is well suited for the compressible and supersonic phenomena. This can be clear, and we have a publication upcoming with some more test cases and some comparisons. It has to be said also, though, that as we see in many other talks as well, the question arises: how can we compare the results, and what's the downside and the upside? And I think that we arrive at the point now where we should compare. In some way, not implementation specific, but somehow be able to compare the methods better, because always, I mean, this is now, the method is proven, you can use the code, it's open source, but, and I think it's also in the, I'm not sure if it's in my references, but you can find the code online, it's called Natrium, it has been presented before, and it's quite, it works quite well. But the question in the end becomes, on the one hand, is the method actually good? I mean, this has been proven, and this has been proven for many other methods as well. But then again, the practical question, and you mentioned it as well, is for the application. What do we need, and how well does it perform? And there we need to arrive at a stage where we can actually somehow balance out. And so I cannot comment on this. Unfortunately, this works very well. It did not take too many computational resources, considering how difficult the case is to simulate. But of course, this is something that has to be mentioned in the outlook, I think. And so I have some references for you. This is mostly the literature I compare with, but also here in the bottom, you see the curvature rules. This can be interesting for those of you who use a mesh-independent method, so a grid-independent velocity discretization. So once you have that, you can actually imply those curvature rules. So thank you very much for your attention, and I will take questions now. Yes, Ali.
How much temperature ratio?
Oh, I don't know. I cannot tell you, but do you mean how high the temperatures can? So the one I use here.
Higher you want quadrature, the more limited you get in terms of temperature you can handle.
So it is still more stable if you. So one case we did was we had to cool the domain a little bit so that we don't go much higher than 1 with the temperature. In the end, we arrived at like lowest temperature 0.8, the highest temperature 1.4, 1.5. So this would be a ratio of like 1.5. I do not know though if it's unstable at some stage. I did not run into this issue at all, however. So I think maximum temperature here, it's a similar ratio, 0.8 to 1.5, but I don't know actually. I can look at, we can have a look later and see if we can find out. Yeah. Yeah.
So it's the limitation is in the temperature ratio. Pierre wants to do it. Someone said yes. I don't like when it's warm. It has to be 2,600. Other questions? And you try to, sorry.
You tried to, so you were mentioning that you didn't have benchmark, but you have a number of benchmarks that you could compare with other codes and so both precision and computational cost, maybe some relevant benchmarks.
So for the mixing layer, unfortunately, it's not clear for the numerical results.
The one I know, at least, but
Okay.
it's like that. There's actually one example.
Yeah, that would be great. Yeah.
So that's
Yeah, that's a good proposal.
Do you have to do something for your method to be conservative, or is it not really conservative?
It's not conservative because of the interpolation that you do. That's the issue that you always have with the sort of semi-Lagrangian or somehow interpolation-based things. I think I brought it. In this case, we have some loss of mass, but it's not so much. So this is a loss around 5% over the whole simulation for the highest Mach numbers. But it does exist, and in some cases it can fluctuate as well. So it does not always go down, but it can go up as well. So this is of course a disadvantage of the interpolation, but it's in a range that we could say that we can live with it. Yeah.
Did you check whether the solution changes with CFL?
Actually, I chose a CFL that's still quite small, considering what we can do. CFL just of 1, and the solver is supposed to handle well up to 2, maybe even above. I did not check this. I should have maybe, because like this I could have saved a lot of computational time. But I was happy once I got the whole thing implemented, and once I had all the results, because it did still take 7 hours on the cluster. So I did not want to use again the expensive resources, just to check this one thing. But for next case, I will definitely start with a higher CFL number and then see if I can already achieve the results, because it's supposed to be quite good. 15 million. So it's roughly 300 by 300 by 170. 32 nodes. Yeah.
Is it possible that if you look at higher CFL, your mass loss is going to be more pronounced?
It's possible, I think, yes. But then again, the interpolation error should only depend on the grid distances. And so this should be in the same precision, just that the populations that you move, they move further. But the error does not lie in the moving the populations, but in the interpolation of departure points. So I would not expect it to change. It's possible. I did not test, to be honest. I can have a look also if Dominic tested it at one point, but it should be stable.
For us, this works. So for ponds, for example, it works like that.
Yeah.
So the mass loss is quite dependent on the CFL. So
It is. Okay. Yeah.
well, if the CFL is too high, yes.
If the CFL is too high, you lose more.
Yes.
You could also get the opposite. And in the end, if it's dependent on the number of time steps for the given problem, you could get lucky. You never know. Then you make the errors 30 times absolutely.
Yeah.
So you
Yeah.
10 times more.
Yeah.
Anyhow. No questions? Let's thank our speaker again.
Thank you very much.
Thank you.
Thank you.